So the words odd and even are in this section with some of the problems. I know you know what odd and even mean, like in the rest of the world. But in terms of functions, we talked a little bit about the idea of odd and even exponents on our degrees for our functions and what it would do in terms of end behavior. When I was using those words, though, I tried every time to not say even function or odd function, because the word even function or odd function is actually a term that gets used in a specific situation that's not always the same as what the degree is telling you. So when we were talking about odd and even degrees on our functions and talking about end behavior, that's similar to what we're talking about today, but it's not a true odd function or even function as it gets defined. So has anyone heard odd function and even function and remember from back in algebra days what they mean? You've heard them? They have to do with symmetry in functions. When we say even functions, we're talking about functions that are, now this is the one that's closest to when I was saying even degree. Think about your even functions. What do they look like when I have an even degree? They look like parabolas. So they're symmetric in terms of left and right. There's always an axis of symmetry down the middle. Now, when we start adding things to them, they can become looking different than parabolas in the middle, but they always end up, as far as the far left and the far right go, they end up looking the same. So these, though, when we get specific and we say it's an actual even function, it's symmetric, but it's symmetric about the y-axis. So I'm talking about functions that, in terms of where the axis of symmetry is, that axis of symmetry has to be the y-axis. That's what a true even function is. So y equals x would not be.
Oh, y equals x squared.
Yes, y equals x squared would be. So it has to actually be symmetric over that axis. For an odd function, this one's a little bit different. This one has symmetry, but the symmetry is rotational, and the symmetry is about not the x-axis like you would hope, because that would sound nice, but it's symmetry about a line, y equals x. So when I talk about this kind of symmetry, I'd be talking about a function that looks like this. It's not symmetry where I would actually fold it over that line, but it's rotational about that line. So if you think about taking that piece and rotating it downward, it would look the same as the piece in the other half. So these are terms that you're going to hear thrown out at different points, where we talk about odd functions or even functions. Another way to check is to think about the coordinates. In terms of your even functions, because they're always symmetric about the y-axis, if I have a point over here, like let's say this is the point 2, 2, I'm going to also have a point over here that would have to be at the exact same height and the exact same distance away from the y-axis. So if I have a point at 2, 2, I would have to have another point at negative 2, positive 2. So notice that in those 2 points, the x's are opposites. One's positive, one's negative, but they have the same height. They both are up 2. So what you'll see is that people will say with an even function, if I plug in a negative x value, I will get the exact same thing as if I plugged in a positive x value. So if I plug in negative 2 and 2 into the function, the answer would look the same. It'd have to have the same height so that it could end up symmetric about that axis. With this one, the way you can check it is if I plug in a negative value in for x, I actually get the entire function made negative. So your goal, one of your goals, would be to be able to look at an equation and decide if it's odd or even. Not all of them are going to be one or the other, because you do have functions that don't look like either of those things. But your job would be able to look at them and decide if they would be odd or even. So I give you a function like y equals x to the fourth. You're supposed to know what end behavior looks like. And you're supposed to also know, in terms of even or odd, yes, it's an even exponent, but is it symmetric about the y-axis? Does it have symmetry that's actually right on the y-axis? So if I plug in a positive 2, do I get the exact same answer as if I plug in a negative 2? If I plug in a negative 15 and a positive 15, I get the exact same answer. So this one would be an even one. If you look down at the second one, it also has an x squared in it, so it's an even degree. You know it looks like a parabola. But think about plugging in numbers. So when I say I'm going to plug in a number, if I plug in the number 2 for both x spots, would I get the exact same answer as if I were to plug in a negative 2? No, because this second term here will always be the same, but this first term is going to be different, meaning your overall answer is going to be different. So this one is not even. Is it odd? In terms of odd, I said you're supposed to be able to plug in a negative answer, and then the whole function should become a negative version of what it used to be. So if I were to plug in like a negative 2, would I make the entire function be a negative version of itself? No, because if I plug in a negative number, I'll get a negative here. This one would still stay positive. So this one is neither. What about the one down below? You guys agree with them? Need more problems. I think I was going to 30. Where are my other ones? Going with? One person said neither. You guys agree? If I plug in a positive and a negative number, definitely the answer is going to change. But if I plug in a negative number, it is going to actually give me a different result. So this would be a neither. What about that guy up there? Even. Did you try it, or did you know it? How'd you know it? If I plug in a 1 or a negative 1 is what you'd be checking in your head. And they would both come out the exact same answer. Also, that's a parabola. It's just shifted down 3 on the y-axis. So if you think about where the vertex is, you'd know it as well. What about the next one? Negative and positives give us the exact same answers. Those ones I think are easy to tell in terms of trying them out in my head. The other one's a little bit harder to tell. So you look at the next one. Think about a positive and a negative version of the same number. Would make it even. Would that happen? No. Okay, so it's not even. Is it actually odd? Does it have that symmetry? It does. This one's odd. Think about plugging in a number that's negative. That's how I check them in my head. If you plug in a negative number, you're going to end up with the negative version of the number there and a negative version of that number there. Meaning both of those terms will just be negative, or in other words, the whole function is negative of what it used to be. So it's odd without even graphing it. But you could check it if you wanted by looking at what that graph is, and what you'd see is symmetry about the origin there. Okay. Questions? Thoughts on that? Okay. I want you guys to then look at your book and think about 4 more. I want you to look at 27, 28, 29, and 30 with your neighbors and decide what you think. And we're going to check them in a minute. So just think about them, write them down briefly. All right. Thoughts on number 27?
Odd. Very odd.
It is very odd. Very good. Number 28?
Neither.
Good. 29?
Neither.
And 30?
Even.
Good. You are smart. Good. Good. All right. Last thing. I want to just make sure that you remember these, because I know we did these in Algebra 2, but it was very quick, like most things in that class. So we have 2 functions up here, and I'm asking you to write what's called a composite. This is one that they like to test you on. I don't know if you saw these on the M-Step or not. I didn't glance over anyone's shoulders, but they do like to test people on these to see if you remember what a composite is. And this is because we're going to be working with different functions in calc. and there will be times where we're looking at situations within situations. And so we're building new functions based off the information we know. So here we have two little functions called f of x and g of x. And we are doing what's called a composite. So there's notation here. The way you would read A is you would say, I want you to find f of g of x. Find f of g of x. Does anyone remember what it is that means for you to do?
The equation for g of x being for x in the f of x function.
Perfect. That's the order you want it to be in. There is another notation that you'll see. It means the exact same thing. They didn't put it in this section, but they do put it in later in the book where they'll write this. And a lot of people in Algebra 2 get confused and forget between if that's times or if that's something else. When it's an open circle in the middle, it's not a letter O, it's actually like up in the center, but it's open. That means the exact same thing. So I could do that for all of these. But the order was, she said, put the function for g in for x. So I want this whole function to go right there, is basically what you're doing. And you're writing a new function based on what that looks like when it's simplified. So I would put that whole thing in where I see x, and then I would finish the function. And then I could simplify this, though. My final answer would be x squared plus 2. So in part B, can somebody besides Emily do that then? If I think the order. I got x squared plus 2 from simplifying this. So it was x squared minus 3 put in for x, but then I had to add 5 to finish the f function.
When you put in x plus 5 squared minus 3.
So that whole thing, everything that is f, goes where you see the x and g, and then you finish your function. So this was x squared minus 3, but then we have to simplify it too. And then minus 3. Good. That would be a simplified version of that. In C, you're doing the exact same thing, only it says f of g of 0. It is x squared minus 3 plus 5, that's true. But the 0 in there is actually then telling you what you're putting in for x. So they're actually going to be able to get a number for this instead of a new function with an x in it. You're going to get a number by putting 0 into that function where you see an x. So my final answer is 2 if I put 0 in for x squared. Okay. The nice part is for D, just like with C, we have actually already done g of f of x. So we could use the work we've already done with simplifying, or we could plug it in. It doesn't matter if you plug it in at the beginning or the end. That's true. Because he was already able to see that from the simplified version of B. Okay, now we haven't done g of g, but we're supposed to do g of g of negative 2. So that means you're actually putting g, everything that you see for that, inside of itself where you see an x. So if I were to look at that, it says x squared, and actually inside this squared minus 3, I have to put x squared minus 3. So you put the whole thing inside of itself. You can simplify it, but you also are going to end up plugging a negative 2 in this. It doesn't matter if you put the negative 2 in now and simplify, or if you simplify and then put it in. Which one do you think's easier?
There's one right here. So you don't
Like,
have to FOIL.
it's true, we wouldn't have to FOIL if we were getting a number. So if you go ahead and you put in negative 2 squared, you can just do that math. 1 squared minus 3, negative 2. If I have a number I know I'm going to need to put in, typically it is easier to put it in right at the beginning, because then you're dealing with less simplifying with x. So do the same thing with F. F of X. So yeah, he's putting in X plus 5 where he sees the X. And so his final answer is X plus 10. Do you remember seeing these? We definitely did them, but it was very quick.